Hi there, this is Heath. This is the day 14 video for walks in trees. Let's get started. When we talk about a walk in a graph, we mean we're talking about a sequence of vertices that satisfy the rule that every pair of vertices in the sequence is adjacent. So for example, BD is a walk because I can go from B to D, back to B, up down to C, and then over to D. Every pair, D to B, B to D, B to C, C to D, all of these have an edge, and so we can walk from this path. A circuit is a walk that starts and ends at the same vertex. In the graph above, DAC, BACD is a circuit. It starts at D, goes up to A, down to C, up to B, over to A, back down to C, and then over to D. The length of a walk is defined to be the number of edges, which is one less than the number of vertices. If I have this walk from A to B to C, A is the first vertex, B is the second vertex, C is the third vertex, and so the sequence will have three vertices, but we say the length is equal to 2 because we had to walk over 2 segments to complete the walk. So the length is always one less than the number of vertices that we have in the walk. Okay? So let's look at this graph. This is example 1211 in the Joy Morris textbook. Give an example of walks from A to E of lengths 1, 2, and 3. So a walk from A to E of length 1 is this walk right here. A walk from A to E of length 2 starts at A, doesn't go directly to E, has to go to somewhere else, and then to E. For example, A to F, and then F to E. That would be a walk of length 2. There are other walks of length 2. I could go from A to C, and then from C down to E, for example. That would work also. And a walk of length 3 from A to E has to go from A and then goes to another vertex, then to another vertex, and then finally to E. So we could go from A to C, C to F, and then F to E. And that would be a walk of length 3. Number 2, show that there is no walk from A to G. That is, there is no way to get from A to G in this graph because A only connects to the set C, E, and F, and those connect to each other. In fact, the set A, C, D, E, F, A, C, E, and F form a complete graph on 4 vertices. 4 vertices, and every vertex connects to every other vertex. But none of them connect over to G. B, D, G, and H also form a complete graph on 4 vertices, but they don't have any junction that lets you get from one of these graphs to the other one. This graph has no way of getting from A to G. What that means is that this graph is not connected. Because in a connected graph, you can walk from any vertex to any other vertex. So if we want to identify the connected components of G, we just did that on the previous slide. A, C, E, and F form one component, and then the other vertices, B, D, G, and H, form the other component. But there is no interaction between these two graphs. And so each of these is a separate component. Prove that being in the same connected component is an equivalence relation on a set of vertices. This is a term that you should have seen back in discrete math. An equivalence relation has to obey three properties. It has to be reflexive, has to be symmetric, and it has to be transitive. So we have to prove all three things. G is reflexive. Under this relation. Because if V is any vertex in G, this sequence is a walk of length 0 from V to itself. And so V is in the same component as V. And that's the requirement, that we're in the same component. V is in the same component as itself. We'll prove that this relation is symmetric. Let A and B be vertices in G. And assume that they are in the same component. A is in the same component as B. That means there is a walk from A to B, because in a connected component, it's possible to walk from every vertex to every other vertex in the component. Then there is a walk A, V2, V3, V4, B from A to B. But now we have to find a walk from B to A. We just follow this walk in the reverse direction. Then B V4, V3, V2, A is a walk from B to A. And so B is in the same component as A. And then the third thing we have to prove is transitive. For transitive, we're going to assume that A, B, and C are vertices in G. We're going to assume that A is in the same component as B, and B is in the same component as C. Okay? But that means I can walk from A to B, and I can walk from B to C. Then there are walks A, V2, V3, V4, B. And I can't use V again, so B, W1, W2, W3, C. So how do we walk from A to C? We go from A to B, and then we keep going from B to C. Then I'm going to come back up to the top because I'm out of space up here. A, V2, V3, V4, B, W2, W3, W4, C is a walk from A to C. Therefore, A is in the same component as C. That's a lot of writing, but none of these steps were hard. I can walk from any vertex to itself by just taking a walk of length 0, my favorite kind of walk. The graph is symmetric because if I can walk from A to B, then I can walk from B to A. And the graph is transitive because if I can walk from A to B and then walk from B to C, then I can walk from A to B to C. Okay? Some more definitions. A walk that does not repeat any vertices is called a path, and a walk that doesn't repeat any vertices except that it does come back to its starting vertex. The first vertex is the same as the last. It's called a cycle. We require that the length has to be at least equal to 1. A walk of length 0 that is just a dot that doesn't go anywhere, we don't call that a cycle. So we don't allow that to be a cycle. A cycle has to go somewhere and then come back to the starting vertex. So a path and a cycle is a special kind of walk and circuit, but they have the restriction that they don't repeat any vertices along the way. So let's look at some theorems here. Let U and B be vertices in G. If there's a walk from U to V, there's also a path from U to V. So if there's a walk from U to V, that can repeat vertices. For example, if this is U and this is V, and the walk from U to V goes to, let's say, A, then B, then C, then D, then back to B, then E, and then over to V. So that's my walk. How do I create a path from U to V? I cut out the loop from the walk and just go straight to V. Okay? So everybody all right with that? So we're going to prove this using a technique called strong induction. We're going to induct on the length of the path. So the base case. If the length of the walk is equal to 1, if the length of the walk from U to V is just 1, then it has to be the walk UV. So if there is a walk of length 1 from U to V, then it is automatically a path. And therefore, not only do we have a walk from U to V, we have a path from U to V. In the induction step, we're going to assume that all walks of less length in less than K have a path. Let's say all walks of length in less than K from U to V have a path from U to V. And let U W1, W2 up through W K minus 2 comma V. There are K minus 2 W's and then 2 more vertices. K minus 1 W and 2 more vertices. That will be the right number of vertices to have a path of length n minus K. Be a walk of length K from U to V. If this walk does not repeat vertices, then it is a path from U to V, and we're done. If the walk does repeat vertices, like this one here does, where the B is repeated, we're going to delete all of the edges between the repeated B's. Between the repeated vertices. Now that may or may not be a path now, because it could be that deleting one set of edges might still leave, maybe there's another set of repeated vertices further down. And so this may not be a walk, or it may not be a path, but it's now a walk whose length is less than K. This is now a walk of length less than K. And by the strong induction assumption, then there is a path from U to V. So we made the path smaller, and we've assumed that every smaller we made the walk smaller, we have assumed that every smaller walk has a path that we need. Okay? Here's another theorem. Let G be a connected graph. Suppose that there is a cycle in G in which U and V appear consecutively. That is, UV is an edge in a cycle. Then if I delete that edge, the graph is still connected. So in order to be connected, we have to have a path from every vertex to every other vertex. So proof. Let A and B be two vertices in G. Since G is connected, there is a walk from A to B. And then we're going to look at two cases again. If that walk does not contain the edge, UV, then it is a walk in G minus UV. And so we're done. We took a pair of arbitrary vertices. We showed that there is a walk from one vertex to the other in this graph, and so this graph is connected. On the other hand, if the walk does contain UV, so here's the idea. I'm walking from A to B, and somewhere along the way, we hit the edge UV. Okay? If the walk does contain this edge, what we know is that these two vertices are part of a cycle. So I can replace this deleted edge with the rest of the cycle. I can go from A to U, and then around the cycle, and then over to B. Then UV can be replaced with the other edges in the cycle to create a walk from A to B in G minus UV. This walk that goes the long way around from U to V does not use the edge UV, and so we can still get from A to B in this graph even after the edge has been deleted. And therefore, in both cases, we have a walk from U to B, U to V, and so G minus the edge UV is connected. Okay? So let's keep going. A couple more definitions. There's one more definition after this one, but this is getting close to the end. A tree is a connected graph that has no cycles. Here's an example of a tree. It looks like parents that have child nodes, but because there's a hierarchy of parent to child nodes and a child never loops back up, we never have any cycles. Any connected graph with no cycles can be arranged in a tree structure. And a leaf is a vertex in a tree that has a degree 1. If we have a tree, then deleting any edge from the tree disconnects the graph. Let's go back and look at that example that we just drew. If there are no cycles and I delete this edge, then there is no way of getting from this vertex to this vertex anymore. That's the idea. So let T be a tree and AB be any edge in T. This is going to be a proof by contradiction. Assume T minus AB is connected. Then there is a walk from B to A. If there's a walk from B to A, then B to V1, V2, up to Vn, followed by A, followed by B. This edge is not in T minus AB, but it is in T. Is everyone okay with that? And if this is a walk from B that comes back to B, this graph is a circuit. Okay? And if every walk contains a path, every circuit contains a cycle. And that's not allowed because a tree can't contain a cycle. And so that's a contradiction. And since we have a contradiction, we have to reject the assumption, and therefore T minus AB is not connected. And that finishes the proof. If we delete a leaf from a tree, the resulting graph is still a tree. In other words, if I just take off any of the vertices that have a degree of 1, then I just have a smaller tree. How do we prove that? In order to be a tree, we have to check 2 things. It has to be connected, and it has to have no cycles. Some books use the word acyclic to describe that. Let T be a tree, and V be any leaf. Since T has no cycles, T minus V also has no cycles. Right? You don't create cycles by deleting things from the graph. And so taking away that vertex means it has no cycles. T minus V is connected. Since we're deleting something that only had degree 1, there's no vertices on the other side of this vertex that would create a disconnection. Because any path from A to B, where A doesn't equal V and B doesn't equal to V, in T cannot include V because V has degree 1. If there's a path from A to B and it went through V, it would have to double back along that same edge, and then it would repeat this vertex here. And therefore, there's no path that goes from A to B that includes V, and therefore that path will still be in P minus V. So the path from A to B is still in T minus V, and therefore the graph is a tree. And so T minus V is connected. So we showed that it has no cycles, we showed that it's connected, therefore T is a tree. All right. We're almost done. Hold on. Last definition. We say that a graph is bipartite if we can divide its vertices into two disjoint sets so that every edge in the graph connects a vertex in one of the sets and a vertex in the other set. Informally, a bipartite graph is one in which the vertices form two teams and every edge represents a playoff between a member of one team and a member of the other team. Here's an example of a bipartite graph. If the top four vertices are all on team X and the bottom four vertices are all on team Y, then every edge goes from a vertex in team X to a vertex in team Y. There are no edges that connect team Y vertices to themselves, and there are no edges that connect team X vertices to themselves. Bipartite graphs are useful in electrical engineering. Where they represent, the teams represent charges, like positive and negative charges, and you do not want a wire that connects two charges of the same type, for example. And so you check for this bipartite condition to make sure that every connection connects two vertices of opposite polarity, for example. So there are other applications for bipartite graphs, but they're pretty useful in electrical engineering. We have a theorem that says a graph is bipartite if and only if the graph contains no cycle of odd length. So this is an if and only if proof. So we have to do two directions. So one we have to show is if G is bipartite, then G contains no cycle of odd length. We're going to prove this by contrapositive. And the contrapositive is if G does contain a cycle of odd length, then G is bipartite. Well, here's the problem. If we have a graph that is of a cycle that is of odd length, then one of the edges will have to connect two vertices on the same team. So if G contains a cycle of odd length, then G is bipartite. Let V1, V2 up through V2k plus 1. Actually, if the length is odd, the number of vertices is 1 greater. So the number of vertices is even. Except that V2k is the same thing as V1 because it's a cycle. Sorry about that. Got a little confused. The cycle here, if I call the vertices A, B, C, the cycle is A, B, C, and then back to A. So there are 4 vertices in a cycle of length 3, but the first one and the last one are the same. So let this be a cycle of odd length. Then VK and VK plus 1 must be in opposite sets. For all, actually I shouldn't use K here and K here. So I'll make this one a J for all K. So V1 and V2 are in opposite sets, V2 and V3 are in opposite sets, V4 and V5 are in opposite sets, so on and so forth. This means that V2J minus 1 and V1 are in the same set. And so G is not bipartite. I can have the edges be in opposite sets until I get to the very last edge, and then the very last edge has to be between 2 vertices in the same set. So then we go and prove the other direction. If G contains no cycle of odd length, then G is bipartite. Okay? So here's an idea behind the proof. Here's a graph that contains no cycles of odd length. It does have a cycle, but the cycle has evenly. I'm going to just pick a vertex at random and assign it to the first set, call it set X. I'm going to assign its neighbors to Y, then assign the neighbors of a Y vertex to X. So this Y connects over here. This will be an X. This y connects here. This will be an x. This y connects up here. This will be an x. And then assign every x neighbor to a y until I have fanned out from my starting vertex and labeled every vertex in the graph. Either every vertex gets labeled or I reach a contradiction. And if I reach a contradiction, that contradiction will be a cycle of odd length. Okay? So pick any vertex in G and assign it to set X. Let's call this vertex V. Pick any vertex V in G and assign it to set X. Assign any vertex whose shortest distance from V is odd to Y, and any vertex whose shortest distance from V is even to X. Okay? Either this works and we have a bipartite graph, or we have an edge between two vertices of the same type. Okay? If this results in two adjacent vertices A and B in the same set, here's where we're going to create an odd cycle. If they're in the same set, then the distance from A to V will either be odd or even, but the distance from B to V will also be the same parity. And so then A to V to B, and then back to A. A to V will be odd, and V to B will also be odd. And then B to A will be one extra edge because they're adjacent vertices. And so odd plus 1 is odd. Or A to V is even, but V to B is also even. And then B to A is one more edge. And even plus 1 is also odd. Then it is a cycle whose length is, okay, I've got to go up here and finish this up, either odd plus 1, or even plus 1. I'd spell that wrong, even. Odd plus 1, or even plus 1. In either case, it's a cycle of odd length. And therefore, it does not result in two adjacent vertices having the same set. This is a contradiction. And so G is bipartite. Whew. Sorry about cramming that in at the end. But here's a corollary. All trees are bipartite. Easy reason, proof. Trees have no cycles of any length, including no cycles of odd length. Therefore, they have no cycles of odd length. And therefore, all trees are bipartite. Okay? What we're going to start looking at next time are algorithms for traversing a graph. You may have heard of these in other classes being described as things like depth first search and breadth first search. We're going to talk about these algorithms from a graph theoretical standpoint. That will be on Friday's class. Thanks for bearing with me.